Hi. I've recently had an influx of new subscribers, and welcome to everybody. But the bump recently was in no small part to Dave Jones, who gave a little bit of exposure on his channel and his Twitter feed. And I'm very grateful for that. If you're not familiar with Dave Jones and his channel EEV blog, stop watching me right now. Go watch him, subscribe, like everything. I'm no expert. I don't pretend to be an expert. I'm learning as I go here. So if you like the train wreck, you can stay here. But if you want to watch a professional, go watch Dave. Today I want to get into the ALU and some addition operations. I want to be able to add a couple things together. Seems like a reasonable thing for a computer to do. Get a 16-bit processor with what's going to be a 16-bit ALU, but I've got some challenges, and I want to walk through those challenges with you today. So let's get into it. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. Let's start our conversation today with the 74LS283 4-bit adder. I considered putting together a number of exclusive OR gates and ANDs and the like in order to implement an adder myself. Unfortunately, anything that I do is going to end up being far slower than this dedicated IC. And with the ALU speed being the component that I am most concerned with, especially related to calculating the flags at the other end of that, I figured it's better to go with a dedicated IC specifically for performing addition and, of course, subtraction at the same time. So the 74LS283 adder takes 4 bits of input from an A side, 4 bits of input from a B side, plus a carry in, and performs an addition of those 3 components and results in a 4-bit result with a carry out. Now I've got the 0, the overflow, and the negative flags indicated in here. The adder itself doesn't calculate those. I have to calculate those based on the results. Z is relatively easy to calculate. It's just a NOR of all of the result bits. Negative is easy to calculate. It's just quite literally the most significant bit. But overflow is a challenge. More on that here in a moment. Okay, now if I wanted to extend this to be a 16-bit adder, of course, that would just scale to 4 individual ICs that were chained together, and that would give me the inputs and outputs I needed for all 16 bits. Once again, 0 is relatively easy to determine. It's just a NOR of all 16 lines. The negative flag is, again, trivial. It's just simply the most significant bit. But overflow becomes a challenge. And it's all in the definition of how you can calculate overflow quickly. Let me explain. So the overflow flag can be calculated based on the carry flag going into the sign bit compared with the carry flag coming out of the sign bit. And if you take an exclusive OR of those 2 bits, when they are different, it indicates that an overflow has happened. And I've done a little research online trying to determine the fastest way to do this, and there are several websites that quote this method. I've got one of them down here in the footnotes, and I'll link to that in the description as well. But that's ultimately what I am struggling with, is how to calculate overflow quickly. Now I can do it based on all kinds of other things and kind of duplicate some of the logic related to the most significant nibble, or I can somehow manufacture some visibility to that carry flag going into the sign bit, or that most significant bit. Let me show you what I'm thinking. Let's assume for a moment that I could move all of these bits to the left one, adding a 5th adder into my setup. This would leave 1 unused bit down here at the bottom on both the inputs and the result. This would also leave 3 unused bits up here at the top, both in the inputs as well as the result. But more crucially, it would give me access to the carry flag going into the sign bit. So that change then would almost trivially give me access to that carry bit that I need going into the most significant bit, or that signed bit, and the carry bit coming out of the most significant bit, and the signed bit. That, of course, assumes that I can preserve that through the 3 unused bits of the result. Now, I mentioned I have a challenge, and the challenge is based on last video where I had problems with the propagation delay from one counter IC to the next, expanding through all 16 bits. There's a pretty good chance I'm going to have a propagation delay here, especially having 5 ICs now that I have to go through instead of just 4. And I believe that it may end up costing me some performance. I'm not certain. As with anything, there's a lot of testing that has to go, and testing in time will be the only way to determine if this is going to be adequate or not. Now, I mentioned that I need to find a way to preserve that carry bit as it goes up through the remaining 3 bits of that last adder in order to make sure that it's preserved coming out. I present to you the magic sauce. This is a truth table of adding 3 bits and getting a 2-bit result. A and B inputs plus a carry in result in a sum of the A and B bits plus a carry out. And so what I want to call your attention to is the row where if A and B are 0 and 1 respectively, it preserves that carry bit. Now the sum itself gets discarded. What's important is the carry in for that particular bit of addition is the same as the carry out for that bit of addition. Now, whether A is 1 and B is 0 or A is 0 and B is 1 is really irrelevant because it actually works for both. The important piece is that one of the inputs has to be 0, one of the inputs has to be 1, and that will allow the carry to be preserved and passed on up to the next bit. And that then is the trick that I'm going to need to use both at the least significant bit and the 3 most significant bits. Let me show you in CircuitVerse. Okay, so what I have here is what I guess traditionally, if you want to call it that, a 16-bit adder with 4 74HC283 ICs hooked together would be. Before I get into that, I actually did take the implementation of the adder and I put it into CircuitVerse as an IC that I can then use in my test setups here. And what's important here is that if I take and turn on bit 14 on A and 14 on B, this being the result here, the most significant bit, if this was a signed integer, is set, but I have no easy way to calculate this overflow flag. Now, if I take a look at my extended adder, which has 5 of these 283 chips, you'll notice that on input A, and I know it's kind of tight to see here, so maybe I can zoom in a little bit. You'll notice that on input A, I've got 1 set to 0. Input B, I've got the least significant bit set to 1, such that if I turn on the carry in, the least significant bit output is turned on. In other words, that carry has been preserved up to what my least significant bit would be, which is actually the 2nd bit up now. So if my least significant bit on both my A input and B input plus my carry, you would expect the result to be 3. And as you see up at the top, the 2 LEDs are lit, indicating binary 3. We can also come down here and take a look at bit 14. If I turn bit 14 on here and bit 14 on there, you'll notice up at the top, my most significant bit, this being the carry bit over here, my most significant bit is turned on. But what I now have is visibility to this carry in for the most significant bit and the carry out from the most significant bit, and I can compare those and trivially determine that I have an overflow. Now again, I've got A's set to 0 and B's set to 1, which allows that carry flag to come all the way up to the top. This is what I plan on implementing. And actually I need to build both the 16-bit adder traditional and the 16-bit adder shifted or extended so that I can test timing between the two. Let me grab some breadboards. Okay, let's try this again. This is the 3rd time I've tried to put this together. In all honesty, the first time I recorded it, I did not like the way it turned out. Filmography, if you will, was just horrible. The 2nd time I tried to put it together, I didn't like the way it turned out. The description was absolutely terrible, and there was no way I could combine the two of them. 3rd time's the charm, right? This is the data sheet for the 74LS83. Now it is both electrically and functionally the same as the 74LS283. The difference being the pinning. And if you look here, VCC is the middle of the bottom row. Ground is up here, the middle of the top row. It does not match any of the conventional logic ICs. I would use the 283, but I only have 2 of those in my stockpile. I've got close to a dozen of the 74LS83 chips. So for my testing here, I'm going to use the 83, but I will convert that when I go to PCB to use the 283 so that I can have more realistic pinning. Like I said, I've made an attempt here before, and what I've done is I've extracted my clock off the main build. Now, I may regret that, simply because trying to get that hooked back up is going to probably give me some trouble, and I'll have some debugging to do related to that. But I needed a clock circuit in order to perform this test. And this clock signal here is going to end up being either all ones being added together all the way across, or all zeros being added together all the way across. More on that in a second. And then I've got 16 bits of output up here. This fancy stitching up here is just literally tying everything to ground together, and I've got a ground connection on both ends just so that I can present ground to the other side of these LEDs. Okay, that orients this. The other thing here, if you take a look here at the data sheet, and I'll probably put a copy of it up there in the corner as well, what I'm actually looking at. So for an 8-bit addition, it takes typically 25 nanoseconds to complete. For a 16-bit addition, it takes 45 nanoseconds to complete. And well, what that tells me is that I should be able to predict what my anticipated 20-bit addition should take, and that should be 55 nanoseconds. We'll see how close we get to those numbers. And I'll stick the pin diagram up in the corner up there, but I need this handy so that I can actually refer to it, because if I don't check every single connection as I make it, the problem is going to be, well, it's going to be that I get the pinning wrong. So I'm going to start with hooking my carry in for the least significant nibble, which is here, and I'm going to tie that to ground, just so that I have a definitive value on it. And then I'm going to take the carry out here and tie it to the next carry in, and then chain that all the way up to the point where I take my final carry out, and this is going to be my measurement point as to when the addition is completed. The next thing I want to do is I want to take 16 of the outputs, and I want to tie them up here to the 16 LEDs. So again, I've got to look at this. Sum 1 is here. Sum 2 is just to the right of VCC. Sum 3 is pin 2. And sum 4 is pin 15. So that should be right there. Same thing for the next nibble. Okay, the last thing to do here, I'm going to apply power as I do this so that we can determine when we end up with an issue with my inputs here. So basically, I'm going to start with A1 up here, and then I'm going to use these little tiny hookup wires here for this, as much as I can anyway. So A1 to B1 are going to be tied together. And so now as the clock cycles, you can see I've got 0 and 1 here on the output, and this is the second bit in. So adding the two least significant bits together yields either 0 or 2, depending on if the least significant bit is a 1 or not. And then I'm going to take from here, well, let's do this. Then I need to go from pin 7 all the way over to pin 4. And pin 4 to pin 3. And now you can see the 3 bits being added there, carries being carried off, but it's not. No, I need to get 4 in there. So let's see here. Pin 1 gives me 4A, and then from there to 16 gives me 4B. That's better. Now, move over to the next IC. Okay, so here's the end result here, is that when my clock line is low, I'm adding 0 to 0, and obviously the result is 0. When my clock line is high, I'm adding all 1s to all 1s, and that's effectively the same as shifting to the left 1 bit, so this bit here is 0, and my carry bit off the end right up here will be 1. And so on the rising edge, what I get on the rising edge of the clock here, the time it takes for this between this rising edge and this rising edge should tell me exactly what my propagation delay is here for 4-bit adders or 16-bit add instruction. All right, I'm more happy with this. Let me get this edited up. I'm going to grab the scope after this and we'll see if we can test the timing. Okay, first thing I want to set up here is I want to look at the clock itself, and I want to set up my triggers here. So get the clock line plugged in here, and let's get that off of auto because that's going to be annoying. Okay, guess it really doesn't matter where that trigger point is. Now I'm at 10 milliseconds per division at the moment. I'm going to end up zooming in because when I plug this second trace in, it's likely going to look like it's sitting right on top of each other. So I will drop this in here and then drop that up there. And yeah, true to form, they look like they're right on top of each other. So as I zoom in, this is 1 millisecond per division. I'm still right on there. Let's put this right on the line here. Now I'm at 50 microseconds per division, 5 microseconds per division, 250 nanoseconds per division, but now at 50 nanoseconds per division, I lose it there. So 50 nanoseconds per division, if I stop it here, turn on my time cursors, and I measure now, I'm going to try to get it lined up to where the trigger point is. This is showing 30 nanoseconds. It's a little faster than I was expecting. I was expecting 45, but I will take that. I will take that win. That's a little bit farther down. Yeah, 33 nanoseconds per division. It's a little faster than I was expecting, but that looks reasonably consistent right there. All right, well, I'll be honest with you, the speed difference there has me thrown a little bit. But next up is I want to get this 5th adder installed, and I'm going to stick it right here, which means that I really want to put this here and pull this out so I've got room to place it. And I'll drop it right in that spot. Power up here, ground's going to be a bit of a stretch, just because of my... No, I think I can actually get that right there. Ground is there. All right, let me bring my data sheet back in here so I can at least look at it. And now I have to go through and I have to move each one of these output LEDs down 1. So my bit 1 here has to come out to sum 4. Incorrect. It has to come down here to sum 2. I hope y'all are screaming at the screen because I've got this totally wrong and that would have caused me all kinds of problems. This is what I get for trying to get ahead of myself. All right, pin 5, which is this one, is power. All right, so output or sum 2. Next one up becomes sum 3. Next one up becomes sum 4. Over here on this side, I have all of these bits need to be tied together. Up here on this side, I can remove most of these. This is my new carry out measure point. So down here, that's A4. A4 can tie to A3. A1 is going to be 0. B1 is going to be 1. Those are going to be hardwired. Now, my carry now has to come off of here as well, so I'll be setting this down here. Up here, I've got A1 and B1 that need to be tied together. This is A2, so that comes off. A1 and B1. Okay, so then now, if I plug this in and I've done everything right, what we should see on the output up here is exactly the same thing we had with just the traditional 16 bits. And we are. So that's good. Now let's get the scope out again and remeasure. Okay, there's my clock. And the next one is going to be measuring against that carry bit. And again, that looks somewhat reasonable. Let me stop it. Put my time cursors up here. And that's showing 28 nanoseconds. Something is definitely not right. Because it can't be slower. I'm sorry, it can't be faster, I should say. But amazingly enough, it might be. Yep, pretty much all this proves to me is my scope sucks. Definitely got to work on that. All right, so I'm now sitting at 36.5 nanoseconds. I don't believe there's a 3.3 nanosecond improvement. I'm not measuring apples and oranges at this point because I'm pushed in a little bit farther than I was previously. So I'm at 25 nanoseconds per division instead of 50 and trying to do this measurement. So I'm of the opinion that while the time difference is negligible, I'm pretty sure that once I get this in circuit, it's actually going to behave far closer to the way I predicted it. So with that said, what I need to do now is extract this board here, the center board, from the build, clean it up. I'm going to pull my A side over here to be 16 bits along the bottom edge here. I'm going to pull my B side up here to be 16 bits along the top side of the rows here, and work on getting all of that wired up. Because reality is I'm going with this. If you've got any thoughts about what I've done wrong other than using an oscilloscope that's inadequate, let me know. Okay, while I'm working on my metallurgical origami up in the corner there, I wanted to give you a sense of just how far out of my depth I am here. This is video number 60, so let's assume for a moment that each video is 30 minutes long and I'm not doing anything like fast forwarding or anything of the like to try to get through any of this build any faster in video form. It's a stretch, I get it. But let's assume for a moment that each video is 30 minutes long. It means I've got somewhere in the neighborhood of 30 hours put into this build in a hardware space. Well, one of the things I wanted to do as well as part of this project is to create an emulator for it. And as you can see up on the screen by the directory that I'm in, I've started that. And if I load up the binary output, this is the actual code that I would burn onto the EE prompts. If I was to load that up and execute that, I now have the start of an emulator. I've got my R1 register, I've got my PC register, and then I've got my fetch register all identified on the left-hand side. I've got my instruction register identified on the right-hand side, and that is what would be executed. So if I hit the spacebar to start, it starts executing instructions, including the initial no-op and the instruction suppress because of a constant being loaded. And what you can see up in the upper left-hand corner there is the lights turning on one at a time, just like the Larson scanner was in real hardware. Now this is brute forcey. I've not done anything cute like identify each of the individual gates and get those coded in. This is strictly an emulator to see the code actually execute. Ultimately, I would like to have this broken down into what happens on the rising edge, what happens on the high level, what happens on the falling edge, what happens on the low level of the clock cycle. And in doing that, what I would prefer to do is actually load up the control ROMs themselves to be able to handle all of that logic, which means that it would be a far more faithful representation of what happens in real hardware. I also have this set up so that once the program counter loops around to the 64 bits that, or the 64 address spaces that I have, it loops back to 0 and starts over again. Again, that's hard coded. But I do have now a representation of my computer in software, and this is going to happen in parallel somewhat with the hardware build out. As I add another register to the mix, I'm going to improve the emulator as well. Now, I started this segment with a description of 30 hours of work on the hardware. I am using Ncurses here as my library for painting this screen, something I have never used before. And with only a simple manual downloaded onto my computer, I was able to put this together in about 4 hours on a plane. So this should demonstrate just how far out of my depth I am here with the hardware and how much I'm actually learning as I go along here. This code is available on GitHub, and I'll have a link to it in the description. Okay, so this then completes the wire up of the actual adder itself. Now you can't really see all of the ICs down here, and you certainly can't see anything that's labeled to tell you exactly what it is. But I'm hoping that I'll recall that this is actually the adder. I've got my carry input here. I've got some more management to do on that because in some cases the carry is going to be forced to 0. It's going to be forced to 1. It's going to be the carry from the previous operation, what have you. My carry output is here, and so I'm just going to bring this up here to get it out of the way. And then I've got the LEDs still hooked up, and simply because that gives me the points for connecting the output. This will end up ultimately going into line drivers to drive the LEDs and then hooked back out onto the main bus, and likely through a latch chip as well. But that'll be a video for a different time. Now, in the next episode, I'm going to work on the R1 register and get that replaced with the new PCB. That's going to require me to test everything again. Now, from video 59, there was a problem with the backplane power. I want to go back and address that. There was some power distribution cleanup that I need to deal with as well. And that first R1 latch wasn't responsive. It didn't actually latch. And rather than troubleshoot it with the old PCB, I want to troubleshoot that with the new PCB and make sure that's working properly. That was the very first latch that took place when we were actually running the CPU. So I want to make sure that that's actually happening. Since I already soldered up one of the register PCBs, I'm not planning on doing that on video again. So I will solder it up off video. It took me 3+ hours to get that done the first time. So hopefully it'll go a little bit faster when I'm not managing a video at the same time. And then I'll get that ready to go, and then you'll see it already soldered up as I'm hooking it up into the build for the first time and pulling the old R1 register out. So that will be the next video. Look for that coming up soon. Again, my cadence, because of the off-camera work and the amount of time it takes to pull things together, the cadence of my videos is a little bit different. So I apologize for that. It's not the cadence I would like, but unfortunately, I just don't have the time. I don't do this as my day job. This is a hobby for me that I am actually putting out on video. And so because of that, I have other things that draw from my time as well. I hope you understand. We'll see you soon.